So now I'm going to have a go at the next lesson in Codility. It's called Count Semiprimes. It's in lesson 11, Sieve of Eratosthenes, something like that. Okay, let's get straight into it. Okay, a prime is a positive integer x that has exactly two distinct divisors, 1 and x. The first few prime integers are 2, 3, 5, 7, 11 and 13. A semiprime is a natural number that is a product of two not necessarily distinct prime numbers. The first few semiprimes are 4, 6, 9, 10 and that list there. So 4 is 2 times 2, 6 is 3 times 2, 9 is 3 times 3, 10 is 2 times 5. Okay, so if we can take two primes and multiply it, we get a semiprime. You're given two non-empty arrays P and Q, each consisting of m integers. These arrays represent queries about the number of semiprimes within specified ranges. Query K requires you to find the number of semiprimes within the range of Pk and Qk, where 1 is less than or equal to Pk, is less than or equal to Qk, is less than or equal to n. For example, consider an integer n is 26, and arrays pq are that we have p0 is 1 and q0 is 26. Then we have 4 and 10, 16 and 20. The number of semiprimes within each of these ranges is as follows. 1 to 26 we have 10. Those are the 10 there. 4 to 10 we have 4, and 16 to 20 we have 0. Write a function that, given an integer n and two non-empty arrays P and Q consisting of m integers, returns an array consisting of m elements specifying the consecutive answers to all the queries. For example, given these three queries, the function should return 10, 4, 0 as explained above. Write an efficient algorithm for the following assumptions. N, which is the maximum number, is in the range of 1 to 50,000. M, which is the number of queries, is in the range to 1 to 30,000. Each element of arrays P and Q is an integer within the range of 1 to n. So that's just telling us that n is the maximum number, and pi is less than or equal to qi. Okay, so let's just do this. I'll just set up the class. Okay, so I've just set up the class and put in the question that, put in the example in the exercise description. So we want to look at 1 to 26, 4 to 10 and 16 to 20, and we expect the answer of 10, 4, 0. Okay, so I think the first thing I'm going to do is work out what the prime numbers are between 1 and n. Then the next thing I'm going to do is work out the semiprimes, but I'm going to make an array of length n, and in that I'm going to the index of the array will be the number that we're questioning, and if it's a semiprime I'll set that number to something, and then I'll work through that array and I'll count up the semiprimes, and then when I come to ask the questions I'll look at how many semiprimes we've seen at this index and look how many we've seen at that index and see the difference. I think I've got a rough plan So the first thing I'm going to do is work out what the primes are. What I'm going to do is I'm going to make a Boolean array actually called primes. I'm going to make that with a length of n. Now the value at the first index, or the Boolean value, these are all initialized to false. Because they initialize to false, I'm going to say that false, I'm going to call this not primes, because first they're going to initialize to false, then I'm going to loop from, I'll just call it A, from 2 to n over 2, and in this not primes Boolean list, I'm going to set it to true if it's a multiple of this. So for A is 2 to n equals 2, and for B equals A, B is less than or equal to, is less than n, B plus equals A. So the first loop I'm going from 2, incrementing 1 at a time, so I'm going to go 2, 3, 4, 5 up to n over 2, and the second loop is going to go what A is, so first it'll be 2, and then it will go 4, 6, 8, 10 until it gets to n. And what I'm going to do is not primes B equals true. So I'm saying that this index is not a prime. So 2, 4, 6, 8, 10, they're not primes. And then 3, 6, 9, 12, 15, they're not primes. And then 4, 8, 12, 16, they're not primes. So at the end of this, I'm left with a list from, I'm going to make this array 1 extra actually, and so the index is the number rather than the index minus 1, so the first value will be 0. A is less than n over 2 B is less than or equal to n, B plus plus not primes equals 0. Now I'm going to make a list of prime numbers using a list of integers. So I'm going to loop through my list of not primes. I know 1 isn't. So now I'm going to go from 2. A is less than or equal to n, A plus plus, and if not primes at A is false, then it's a prime. Primes add A. Okay, so far what I think I've done is made a list of prime numbers. Now the next thing I'm going to do is find the semi-primes, but first I'm just going to check that we've done that. So I'm going to return null and debug it so far. So we're going to give it 26, and we know from the description that the prime numbers are 2, 3, 5, 7, 11 and 13. So if I've done this right, this list should contain 2, 3, 5, 7, 11 and 13. So I'll just put a debug pointer there and debug it. Go straight to the end and see if it's worked. Prime 17, 19 and 23. Okay, so let's try and dig in a bit deeper. So A is 2. So first A is 2. And B is going to go 2, 4, 6, 8 up to N. So not primes 2. So 2 is not a prime, remember it's 0, 1, 2. Actually the first one in this is a prime, that's the whole point of a prime. So we're going to go from 1 and we're going to start off as B equals A times 2. Now that's what the 2 is a prime, but 4, 6, 8, 10, 12 is not because of 2. The 3 is a prime, but 6, 9, 12, 15 is not because of 3. So we start off at B being A times 2. Right, we start off at 2. Let's just skip this first step. In not primes we have 0, 1, 2, 3, 4 is not a prime, 5, 6 is not a prime, 7, 8 is not a prime, 9 is not a prime, 10 is not a prime, 11, 12 is not, 13, 14, 15, 16 is not. Let's just see what answer we get from the next section. Primes 2, 3, 5, 7, 11, 13, 17, 19, 23. 2, 3, 5, 7, 11, 30. Okay, I think that's right. I think those are our prime numbers. Now we're going to loop, because there's not going to be too many of these up to N. I'm going to make a similar list, only this time a similar list of semi-primes as what I did with this not primes list, but this time I'm going to make it an int array, because after I'm going to convert it to be the total number seen up to that point. So I'm going to make a list int array semi-primes equals new int array n plus 1. So at 0 I'm going to start off at 0, so that the index of the array is the number that we're thinking about. That's just to stop it being confusing. And I'm going to loop. Now, there shouldn't be too many prime numbers, because I think they start spacing out as we go along, so I don't think this is going to be too efficient. But I'm going to start off at 2 and then multiply that by 2, 3, 5, 7, and then I'm going to go to 3, multiply that by 3, 5, 7, 11. So my first number in the loop is going to be the first index of the primes array, equals 0. A is the subprimes size minus 1, A plus plus. So I'm so used to using I as an index. And B is going to start off at A. B is the subprime size minus 1, B plus plus. and the product of A and B is A times B. So semi-primes A times B I can say, I can abort this if A times B, A times B is less than semi-primes length. So as soon as we've gone out of the range, for example, if we do 13 times 13, we're well over the limit of the of M. So semi-primes A times B equals 1. So let's have a look at what the semi-primes were. The semi-primes we're expecting to see is 4, 6, 9, 10. Just put that in a comment. Make these comments a bit more sensible. So semi-primes are 4, 6, 9, 10, 14, 15, etc. A equals 0. A is less than prime size. A plus plus. B equals A. A times B is less than semi-prime's length. These are the indices. So B should be just like that, but if A times B is greater than semi-prime's length, greater than or equal to semi-prime's length, then we can break the for loop. Okay, I need to say in prime 1 equals primes get A. Actually, just to be consistent, I'll call it prime A, and prime B is primes get B. And then if prime A times prime B is greater than, is out of our range, then break. Otherwise, semi-primes at the product of prime A and prime B equals 1. Debug again. So now semi-primes, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, 11, 12, 13, 14 and 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 and 26. Right, now I want to turn this list into the number of semi-primes we've seen up until the point. So I want it to be 0, 0, 0, 0, 1, 1, 2, 2, 2, 3, 4, like that. So I'm going to loop through this list. From 0, it's less than semi-primes length minus 1, I plus plus. I'm going to say int counter equals 0. and then semi C plus equals semi-primes at I and semi-primes at I equals C. So now let's have a look at our semi-primes array. We've got 1, 2, 3, 4, and then 5, 6, 9, 10. Okay, so that's done what I want. Got a 1 at the end. Less than, not less than, not equal to. So at the end we have 10. Okay, now the reason I've done this is when we want to ask it the questions like 1 and 26. If we look at semi-primes at index 26, we should have 10, and at index 1 we should have 0. So the answer is that minus that. So we make a new array. This is the result. I'll just put a comment. Result. Int array result. New int array, and it should be the same length as P and Q, which should be the same. And for each query, for I equals 0, I is less than P dot length, I plus plus, the answer at I equals semi-primes at P at I minus semi-primes at Q at I, and return the result. So we want to see 10, 4, 0. I'm just going to run it. Minus 10, 3, 0. Okay, I think this has gone wrong at every possible stage. The answer is Q minus P, not P minus Q. 10, 3, 0. Okay, so between 4 and 10. We need to go to -1 on the P query, because if the thing at index of P itself is a semi-prime, then we're not counting it. Index out of bounds. Hang on, that P semi-primes at Pi minus 1. I need to think about going out of bounds there. So we've got 10, 4, 0, but what if we asked it for 0, 0? We've got to give it 1. We've got to give it 1. I think it said in the description that each element of PQ is within the range of 1 to n, so I don't need to worry about going out of bounds. 10, 4, 0, that is my solution. I am a bit concerned that it may not be efficient, but I don't think that there are too many prime numbers as you get up higher, and we're only going to 50,000. It's not that high at all, and all this processing we're doing at the start, and then we're answering the questions quickly, so there may be 30,000 questions. Obviously what we wouldn't want to do is to start working out primes and semi-primes for each query, which would be the easiest thing to do, but we wouldn't want to do that, because then we've got 30,000 questions. We'll have to go through this loop of working out the primes and semi-primes 30,000 times, which is not going to be efficient at all. So I think that is my answer. I'm going to submit that and see how it does. Run the tests. It should work on the test. Oh, we've got some imports to do. Submit task. Let's see how it gets on. %66%. Runtime error. Large random. So we had an array index out of bounds at 42. And line 42 is semi-primes equals prime A, prime B. What are we going? Are we going to possibly 30,000? And 30,000 multiplied by 30,000. Is probably going to a negative value. So I'm just going to cast it to a long there to make sure that if prime A times prime B doesn't overflow back into a negative value. I'll forgive myself for that mistake, and let's just resubmit that. So the problem was when we were finding the product of the two prime numbers, if we had a very large prime number, we were overflowing the integer and going back into negative values, and then trying to set a negative value in the semi-primes array. So let's see if that fixes this. And 100%, so it took me 2 attempts, but I'm reasonably happy with that. I'm sure it sent it some large numbers with the 30,000 limit on the queries, and yeah, all max ranges, so it pushed everything to the limit there. So I'm reasonably happy with that. So that's my solution to count semi-primes in Codility. Thanks for watching.